Welcome my friends, welcome to my next lecture. In fact, I should say that this is my last lecture of this course. So today I hope I will be able to finish the remaining concept. In fact, the concept I have already discussed. So I already discussed in my last lecture regarding what is the statement of what is called Gauss Divergence theorem. Couple of examples I have discussed. Now today I will talk about few more examples or applications, and that will be the end of this course. So today is my last lecture. So I will just start with again recalling the statement of what is called Gauss Divergence theorem. Couple of applications I already discussed, and then I will discuss few more applications, and that will be the kind of end of this concept, and at the same time it will be the end of this course. Okay, so as I said, so let me just recall the Gauss divergence theorem once again. So I already discussed in my last lecture what is the statement of Gauss divergence theorem. So it says that if I start with a solid region in three-dimensional Euclidean space whose surface S is oriented say by positive normals n cap, and if I start with a nice vector field, that means capital F, which is continuously differentiable vector field on some open set containing my region G, then the corresponding surface integral, which is nothing but the triple integral of the divergence of it. So this is the statement of Gauss divergence theorem. So that means surface integral is exactly equal to the what is called triple integral over the region. Okay, so this example I have talked about, that use Gauss theorem. You showed that what is the outward flux of my vector field. Outward flux means the left hand side. That means if I have a vector field, this is the normal component of my vector field A, and if I perform this surface integral, then physically is nothing but the outward flux of my vector field capital A across my sphere x square plus y square plus z square is equal to a square. So you can calculate that what is called outward flux of my vector field what is called across the sphere, which by divergence theorem I can write in terms of the triple integral of divergence. Now you can calculate the divergence, you will end up with this is nothing but the what is called the 4 pi aq divided by 3. This example it's okay. In the second example I said that okay, let's start with a region which is bounded by the hemisphere x square plus y square plus z minus 1 square is equal to 3 square, z runs from 1 up to 4, and you have the plane z is equal to 1. Then you have to use Gauss theorem to find the outward flux of your vector field capital F, which is given this one, across your surfaces S of what is the surface? That surface bounded the region G. And what is that? Again you have to use what is called the left hand side. This is nothing but the outward flux of my vector field capital F across my surfaces. This is nothing but exactly by Gauss divergence theorem the triple integral over my region G by divergence, and you just calculate the divergence of the vector field. It's exactly 3. So 3 will come out. So this will the volume of the hemisphere. So total volume of the sphere is 4/3 by pi 3 cube, but it is I am talking about the volume of the upper hemisphere. This should be 2 by 3rd, and that is end up with the 54 times pi. This is one of the way. Another way you can separately you can calculate it. It says that you just the surfaces you can break up into two parts. One is the upper hemisphere, and in the plane you have the what is called the S2. So that means the S2 is a circular region x square plus y square less or equal to 3, and what is my S1? S1 is the upper hemisphere. So you can break up into two parts, and you can just calculate individually the corresponding integral, surface integral, this and this. Okay. So this is another example. It says that suppose S is positively oriented surface x square plus y square plus z square, means I have a unit sphere with the upper half plane, that means upper hemisphere I am talking about. Then I am saying that calculate this surface integral of this object f dot n cap, that means the normal component of my vector field over these surfaces where vector field capital F is given. Now of course the example I have discussed, this capital F vector field, it is very nice, whose components are functions of polynomials of x and y and z. This is infinitely many times differentiable. In particular it is a C1 vector field. Now look, so this is the surface in this example. It is very nice. It is a surface actually in the upper half. Z is positive, that means upper hemisphere. That means you should not apply the divergence theorem blindly. That's my point. What is the divergence theorem? That means you start with a solid region, get the surface which is bounded, the region bounded by this surfaces. That means I am talking about the closed surface. So but the surface integral I am given to calculate, it is nothing but a closed one, it is the upper half hemisphere. Okay. So therefore if I want to apply what is called Gauss divergence theorem, I have to first make a region and get the closed surface, apply divergence theorem, and then talk about this integral. Okay. How do I do that? So let J be the solid region bounded by the surface S, this is the upper hemisphere, along with the circle of unit radius or region, not circle, it is the region bounded by the unit circle staying in the plane Z is equal to 0. So that means if I include my surface, given surface S along with S1, then this union becomes a closed surface, and what is the interior region? This is nothing but the region G. So therefore, you can apply what is called Gauss divergence theorem. So therefore, so integrations over S plus integration over S1, that means it is nothing but the integrations over the closed surface whose region bounded by the closed surface is nothing but G, which is nothing but by Gauss divergence theorem, divergence of f dv. Now divergence of f you can easily calculate, which is 1. So that means I am talking about what is called the region bounded by the surfaces S and S1, which is nothing but the region staying in the upper hemisphere. That means it is nothing but 2/3 pi aq, where a is 1. So that means 2/3 pi. Okay. But that is nothing but the value of this plus this. But I want only this object in the question. So therefore, I have to calculate this object separately, and if I just subtract from 2 pi by 3, then that will give you the required answers. So that means that what is remaining to show that what you calculate the surface integral of this object over the surface S1. So therefore, this is nothing but this triple integral minus this surface integral. Now you just calculate it. Now you see, in my last lecture I was bit actually I should say confused that, so while I am talking about this is exactly equal to minus x square, but at the same time I have written that unit normal vector is equal to k cap. So now that's why in my last class, if you notice my face, that I was a bit confused, that one hand I am taking n cap is equal to k cap, and at the same time I am having the minus x square, because what is my capital F? You see, capital F is the kth component is x square, right? Okay, so kth component is x square, and this is n cap is k cap. So therefore, if I take the dot product, then it should be x square, right? So then why the minus sign is coming? The point is that it is very nice, because you see that, look at the surfaces. The surfaces, what I want, positively oriented surface, right? So therefore, if I want to apply my Gauss theorem, I have the closed surfaces. So what picture is that? Because upper hemisphere along with the what is called circular region in the plane z is equal to 0, and that closed surface should be positively oriented. That means the normal vector should point upward directions. Now if that is the case, in the upper hemisphere at each point it's pointing upward, that's perfectly all right. But in the what is called circular region staying in the plane z is equal to 0, that's also is a surface, and of course what will be the since it is positively oriented surface, because that is what by default I started in the statement of what is called Gauss divergence theorem. So in the circular region in the plane z is equal to 0, so what is the normal directions pointing upward? That means in the downward directions. Okay, so I have these surfaces, that means since if I start with my surfaces whose positively oriented, that means the point at any point the normal pointing outward from the surfaces. That means the directions of n cap should be that means the directions I should, so that means k cap, so there should be minus, so then pointing upward directions from the surfaces. So that means what will be n cap? This should be, I think it should be n hat is equal to minus of k hat. So there is a typo actually, it should be a minus sign. So that is why I get confused in my last lecture a little bit. So now, so that means this time, so since my surfaces is positively oriented, so therefore my unit normal should be exactly equal to minus of k cap, because at each point the unit normal vector pointing outward from the surfaces. So therefore the n cap corresponding should be minus of k cap. Okay, so it is pointing outward in the surfaces. So therefore, if I take the circular region in the plane z is equal to 0, so therefore what is your n cap? N cap should be in the outward directions from the surfaces. That means it should be minus of k cap. Now if this is n cap is equal to minus of k cap, then it is perfectly all right. It is exactly equal to minus of x square. So that's what in my last kind of lecture I was bit kind of confused why I am saying that n cap is equal to k cap, but still I am getting minus of x square. But it's a typo. It should be n cap should be minus of k cap. Okay. So this is the kind of what surface integral you have to do, and this is perfectly all right because you have a circular region. So therefore, if I make it to a polar coordinate, so that means r runs from 0 to 1, theta runs from 0 to 2 pi, and x square means r of cosine theta, that means r square cosine square theta. And if you change it to polar coordinate, one extra r will be there, r dr d theta. So therefore, you have r cube cos square theta dr d theta. Then if you just calculate it, this integral, you will end up with minus pi by 4. So therefore, what is my required surface integral, which is nothing but this, which is 2 pi by 3 minus of minus pi by 4, and you will end up with the calculations 11 pi divided by 12. Okay. So that is kind of use of divergence theorem to calculate surface integral. Okay, so as I said, I will discuss today bit of a couple of applications of Gauss divergence theorem. What is that? So look, Gauss theorem is applied, Gauss theorem, or I can say that Gauss divergence theorem is applied in deriving the mathematical form of conservations of laws. So Gauss theorem is applied in deriving the mathematical form of conservations of laws. That means the rate of change of the density plus the divergence of flux is 0. So that is the applications one. Second one is that for any closed surface S, this surface integral should be 0. What is that? Surface integral of this one. What is this? This is curl of f, right? So that means what is this? You can write it. This is nothing but integration over S curl of f dot n cap d sigma. This should be 0. Why? And that is very nice. Why? Because your surface, say closed surface, which is very nice, right? Smooth surfaces are positively oriented. I am claiming that for any closed surface this integral should be 0. Now you just apply what is called Gauss divergence theorem. So what will happen? This integration is, this is curl of f, okay, dot n cap d sigma, that I want to calculate. So this is my vector field curl of f, right? So and this vector field, it is of course, if my vector field capital F is nice, continuously differentiable. So curl of f, this is also a vector field, this is also will be nice, okay, it is C1 vector field. Now if I apply what is called Gauss divergence theorem, I have a closed surface S. What it boils down to that, this is nothing but the triple integral over the region G. G is what? G is the region enclosed by your closed surface S of divergence of your vector field. What is my vector field here? This is curl of f, right? dv, this should be. But you know, when I talked about divergence or curl, if I have a vector field capital F, then if I calculate the divergence of curl of f, this should be exactly equal to 0, if you check it. So therefore, since the integrand is 0, so therefore this is 0. So therefore, by simple applications of Gauss divergence theorem, I can conclude that if I take for any closed surface S, the surface integral of this curl of f dot n cap d sigma, this surface integral will be always 0. We just apply Gauss divergence theorem. This integral boils down to the integral, this one, triple integral of divergence of curl of f, but divergence of curl of by vector field is 0. So therefore, this is exactly 0. That is another application. Third one is that it says the relations between this sort of surface integral, where what is your vector field? This is my vector field f of x y z, which is nothing but x I cap plus y j cap plus z k cap, right? This is my vector field, or you can say that this is nothing but x y z, right? This is my vector field. So this surface integral is, and the volume V content within the closed surface S. So this actually surface integral over S, which is nothing but 3 times V. That is also straightforward. Why? Because suppose you have a surface integral, this one, and suppose you have a surface and the region bounded by the surface, so let it be the region G, and suppose the volume of the region is V. Okay. So therefore, suppose you have a surface S and G is the region bounded by the surface S, and suppose the volume of the region G is V. If this is the case, then this surface integral is nothing but 3 times V, and that is easy. Why? Because this surface integral, again, by using Gauss divergence theorem, you can make it to a triple integral over the region G, right? What is the region G? G is the region bounded by your surface S, and what is it? This is then divergence of f times the volume integral, right? But what is divergence of f? If your vector field f, so this divergence of f, if you calculate it, this is nothing but 3, right? Because this is nothing but, if I write it capital F, this is f1, f2, f3, then what is my divergence of f? So divergence of f, this is nothing but del f1 del x plus del f2 del y plus del f3 del z. Now if I calculate it, f1 is nothing but x functions, f1 of x y z, f2 of x y z is y, f3 of x y z is equal to z. So therefore, this is 1 plus 1 plus 1, that means this is 3, that means it should be nothing but 3 times this G times dB. And what is G times dB? This is nothing but the volume of the region G, and that I already said this is nothing but B. So therefore, this is exactly equal to 3B. So therefore, this kind of surface integral is nothing but 3 times B, where V is the volume of the region G bounded by your surfaces S. So this is one of the applications. That is why I am written relations between the surface integral this and the volume B content in the closed surface S. That means you have a closed surface S, let G be the region bounded by the closed surface S. If V is the volume of that region, then this surface integral exactly equal to 3 times B by simple applications of what is called Gauss divergence theorem. Okay. A couple of comparison I should make between Stokes theorems and Gauss theorem. What is that? So Stokes theorem, you see I have written both Stokes theorem and Gauss divergence theorems can be used to evaluate certain surface integrals, but there are some significant differences. What are the differences? It says that number 1, Gauss divergence theorem applies only to surface integrals over closed surfaces. That crystal clear from the statement of the Gauss divergence theorem. That means you start with a what is called solid region in R3 and get the surfaces, that means closed surfaces which enclose that region, closed region G. So, and then you have the relations between the surface integral and the triple integral. So, therefore, first one is that Gauss theorem applies only to surface integrals over closed surfaces. Number 2, Stokes theorem applies to any surface integral. There is nothing like you have to start with a closed surfaces. It's not like that. It is like applies to any surface integral. As long as it satisfies the hypothesis of my Stokes theorem, it is perfectly all right. You do not need to start with a closed surface. No, you just start with some surfaces. As long as it satisfies the hypothesis of my Stokes theorem will be applicable. What about the third one? Third one says that Stokes theorem also applies. Since it applies to any surfaces, so therefore I can apply it in the closed surfaces as well. So you see Stokes theorem also applies to closed surfaces as well. But in this case, what will happen? Suppose I want to apply Stokes theorem in the case of closed surfaces. Now you know closed surfaces means what? There is no boundary points. So therefore there is no boundary curve. So therefore this left hand side integral should be automatically 0. That's what I have written. So but in this case gives only a trivial result. Since the boundary of a closed surface is empty, so both sides of Stokes theorem become 0. What is the Stokes theorem? So Stokes theorem means what? You have a surfaces, right? Oriented surfaces. So then it will have a boundary. Suppose the boundary is C. So oriented surface will imply some boundary orientations, right? So that means Stokes theorem says that integrations or vector line integral of my vector field f over my boundary, which is nothing but exactly equal to the surface integral of the vector field capital F with some integrand. Then in the left hand side, since I am talking about closed surfaces, so therefore it will be 0. And what about the right hand side? Right hand side, if you see in the statement of the Stokes theorem, that vector line integral of capital F over the boundary, which is exactly equal to the surface integral of what? What is the integrand? Integrand is curl of f dot n cap, if you remember. Now, if I start with a closed surfaces, just now I have discussed that for any closed surfaces, curl of f dot n cap is 0. So therefore right hand side is 0, left hand side is 0. So just go back to the statement of Stokes theorem, then it will be more clear. Look, so this is suppose if I start with a closed surface, since it has no boundary point, this is 0, not an issue. And what about this one? For any closed surfaces, I just discussed in my earlier slides that if I take the curl of f dot n cap and then I will apply what is called closed surfaces, so therefore surface is very nice, vector field is very nice, I can apply what is called Gauss divergence theorem, then it will be the triple integral of divergence of my this vector field curl f, and this is 0. So therefore this right hand side is 0 and left hand side is 0. So therefore trivially true Stokes theorem if I start with what is called closed surfaces. That exactly I have written there. Okay. So that is. So Stokes theorem also applies to closed surfaces, but in this case gives only a trivial results. Since the boundary of a closed surface is empty, so therefore left hand side integral is 0. And what about the right hand side? Right hand side is, I already said, for any closed surfaces this integral is 0 and this is nothing but what is called curl of f. Okay. So therefore in that case this is trivially true. So this I think kind of bit of what is called comparisons between Stokes theorems and Gauss theorem. Okay, there could be many, but I just listed very few. So I think that's all from this concept, what is called Stokes theorems and divergence theorem. Couple of applications. So in this concept, I just recall everything for 1 minute. So it says that I am starting with the surfaces, then I talked about smooth surfaces, oriented surfaces, then what is called, gave a statement of Stokes theorem if your surface is very nice, and then I gave the statement of Stokes theorem if the surfaces has holes. Okay. So and then couple of examples or validity of Stokes theorem I have discussed. Then I moved my discussion to what is called divergence theorem. Then I stated the divergence theorem. Then couple of examples I have discussed, and then a couple of applications I also stated. And at the very end, I just compare two Stokes theorems and what is called Gauss divergence theorem. I think that's all for this concept, and at the same time it will conclude the what is called full lecture series. So this is the end of my lecture. So now let me just summarize for the, like whatever happened in this course. So if you remember, I started with from the very beginning. So let me just recall that one. So if you remember, the full course we have divided into like 12 weeks. Okay. So, and each week if you see the course structure, our plan is to discuss about more or less the what is called multivariable kind of analysis, and that was the target. And to do that, we have started with week 1. If you remember, week 1 I think we have started with what is called introduction to vector algebra, very basics, right? Introduction to vector algebra and what is called vector valued functions or scalar valued functions of vector variables or scalar variables, this very basics about the function theory. And then we move our discussions. Initially we have discussed what is called functions of vector variables, and then we talked about the continuity or differentiability or existence of limit. That was then we have discussed, and then after that we talk. So this part is okay, perfectly all right. Like if I talked about like functions, the range is several variable, but the domain is single variable. So this kind of analysis, if you see, it is almost the analysis of what is called single variable calculus. And how you can proceed it is just take the component, right? So if I say functions from R to Rn, right? Suppose you have a functions. So how do you handle that one? R to Rn means you have a functions, so it will have n many components, f1, f2, fn, and you will see whatever analysis I have discussed, like the existence of limit, continuity, differentiability, if and only kind of things, you will see each of the component functions has this kind of properties. So therefore the vector valued functions of real variable will almost similar to the analysis of real valued functions with real variable. However, if I change it to a different one, that means now if I start with say real valued functions of vector variable, there you need kind of little difficulties. Of course, the difficulties we will face, like to talk about like continuity and let's say existence of limit, it's okay. Kind of you can fix. Suppose you are dealing with n variables, you can fix n minus 1 variables and think about a functions 1 to 1. So those kind of concept also you can have parallel to one variable calculus. However, the main difference you will get in the concept of differentiability. There you will have the kind of changes will be there, that is not so common in the case of single variable calculus, right? So there you have the major differences you will get in the case of what is called multivariable analysis. That means if I deal with what is called scalar valued functions of vector variable, and there we talked about what is called partial derivative, directional derivative, then we talked about total derivative, couple of relations we have talked about, that the relations between total derivative or existence of total derivative implies the existence of direction derivative, partial derivatives, what about the converse, what sort of things. So that's we have discussed in the beginning part. Okay. So and then as an applications, once I have this differentiability, and then we have discussed the extremum values of function, that means Lagrange multipliers. So those kind of things we have discussed. So couple of applications part, because this kind of extremum problem or maximizing or minimizing of your functions subject to some conditions, it will be very useful from what is called experimental point of view, like in the like those who are in engineering sciences, for them it will be very useful for the applications of your concepts, like whatever you have learned in the context of several variables, like scalar valued functions of vector variable or vector valued functions of scalar variable or vector valued functions of vector variable. So this kind of functions, so if I know the notions of what is called continuity, differentiability, then or limit, continuity, differentiability, then there are nice applications. So one of the applications, few applications we have discussed, that is extremum values of real valued functions of vector variables, in particular Lagrange multiplier we have discussed. So that will be very useful for engineering sciences. So I hope we have given little bit of flavor in that directions. Okay. Then we move our discussion to the integral part. That means first couple of weeks, I think first 4 weeks we have discussed the differentiability part, or calculus for differential calculus I should say. That means limit, continuity, differentiability, starting with the functions, some examples, couple of things we have discussed, and then we mainly focus on the limit, continuity, differentiability for functions, vector valued functions of vector variables. Okay. And then we move our discussion what is called to the integral part. So that means the integral calculus. So we have started, first we have started what is the notions of what is called double integral. So this is nothing but the Riemann integral, you know, single variable calculus. If I have a functions from closed interval a b to r which is bounded, then the notions of Riemann integral, you know, that you can easily extend if I have a function say from R2 to R. That means if I start with a function say defined on closed interval a b cross closed interval c d to r, suppose that means instead of R to R, I am talking about R to 2R. So instead of interval, what will have? You will have the square. So then how to proceed with the double integral? Then we have just observed, or in fact I have discussed, that the concept of Riemann integral, that means in terms of partitions, you can easily extend to the kind of two-dimensional setting. And similar concept you can also discuss if you have a R3. So more than R3 it will be very difficult, but you can parallelly do that. You can take the partitions, because if I am in Rn, how many intervals will be there? That means it should be a1 comma b1 cross a2 b2 up to an bn. You take the partitions of a1 b1 a2 b2 and n bn, make a partitions, take the norm of the partition goes to 0, then you can define the corresponding what is called multiple integral. Instead of double integral, triple integral, multiple integral you can do. Okay. Then I talked about what is called curves and what is the notions of contour. Then I talked about the concept of line integral, and then once I have a line integral, then I talked about the surface integral. Of course, in the concept of line integral and surface integral, there are many applications are there. So there I have discussed, and then of course I need to introduce the notions of line integral and surface integral to talk about three major theorems, like what is called Green's theorem. First I have discussed, and then I talked about what is called Stokes theorems and Gauss Divergence theorem. So therefore, first couple of weeks we have discussed that what is called differential calculus part. The second half, that means second couple of weeks, we have talked about integral, and then later we talked about as an applications of integral, like what is the famous three theorems, what is called Stokes theorems, Divergence theorem and Green's theorem. And of course, many examples we have discussed. So this is the kind of overall view of this course. But I should say that mainly we focused on the theoretical part. Okay, couple of applications of course we have discussed, but maybe I think from engineering sciences it might, one can expect that okay, more applications should be there. But I should say that at the beginning, if we just look at the structure of the course, it is mainly for theoretical point of view. Of course, we have discussed many applications, many examples, many connections, so that I hope that will be also useful for applications point of view, particularly those who are in engineering sciences. So couple of examples like that, like what is called Lagrange multiplier, and then that couple of theorems we have talked about, Stokes theorem, Divergence theorem, Gauss theorems, and then vector line integral, scalar surface integral, vector surface integral, scalar line integral, vector line integral. Those are also have a kind of many nice applications. So we have also discussed many applications, but at the same time I should say that it has also kind of substantial theoretical point of view. Okay, so that's all the overview of this course, and I hope you people have at least learned a little bit of this course. And if you just go through the content and just look at the slides, you will have some idea about the kind of calculus, multivariable calculus. That means the notions of kind of differential calculus and integral calculus. You are familiar with single variable functions, like functions of real variable with real valued functions. So this course somehow motivate to what will happen in the context of vector valued functions of vector variable, and couple of like comparisons or corresponding notions of differential calculus and integral calculus we have discussed, and mainly substantial theoretical point of view is there. And of course, we have discussed at the same time couple of applications, and I hope this will be useful for some engineering sciences students. And of course, in broad sense, it will be hopeful those who are in the very beginning to learn in the what is called multivariable calculus. I hope this course will be useful for you. Okay, so I think that's all from our side regarding these lectures. So a couple of assignments we have already given each week assignments, and this is related to the corresponding concepts. So try to solve those assignments, and then I hope it will be helpful for your in the exam as well. And I think at the end I should say that okay, wish you all the best for your exams. So do well. So just go through our slides, lecture notes, and try to solve the assignments problems whatever we have given. Okay, and I think that will be okay if you just regular in this course. That means if you are update in week wise in doing assignments and lecture notes, I should say you can do well in your exams. So okay, so I think I should stop here. So that's all from our side regarding this course, and we wish you all the best in your exams. Thank you. I think well, I should say that maybe in next course, if we offer, maybe in next courses I'll meet once again to all of you. Okay. Okay, I think I should stop here, and we both, myself and Professor Guru Prem Prasad, will welcome you, and we hope that you have learned something from our course, and also we hope that you people have enjoyed, and we wish you all the best. Okay, thank you.